Now we're going to look at how to solve a couple of exponential equations. With a problem like this, there are two different ways that we could do this, and I'm going to show you both of them because they both have good points and bad. If we do it using logarithms, which is definitely the longer way, we would take the natural log of both sides, or actually we'll take log base 2 of both sides. So log base 2 of 2 to the x minus 3 equals log base 2 of 0.5. We swing the x minus 3 down, but also remember that 2 to what power gives you 2? That's just 1. So this side just becomes plain old x minus 3. And again, that's because the x minus 3 swings down, and 2 to the first power is 2. On this side, you can, since we took log 2.5, now you do need to either put this in the calculator or realize that log 2.5, that is negative 1, because 0.5 is the same thing as 1/2, and 2 to the negative 1 equals 1/2. So this, whether you just see it or you could put it in your calculator, this becomes negative 1 equals x minus 3. We add 3 to both sides, and x equals 2. Now, alternately, you could, at the very beginning, do this without logarithms with a little bit of insight. And what I mean by that is if you realize that 0.5 is 2 is 1/2, this is 2 to the x minus 3 equals 1/2, which is 2 to the x minus 3 equals 2 to the negative 1. And now, since we have like bases, we can set the exponents equal. X minus 3 equals negative 1, and x equals 2. So either way works. The one way is cookie cutter, but this way is quicker, easier, but you have to realize that that 0.5 can become 1/2, and then that 1/2 can become 2 to the negative 1. So this time we are going to start off. We are trying to isolate the e to the 3x. You must isolate the piece, the factor that has the exponent in it. So we've got to get this e to the 3x all by itself. So we add 20 to both sides. 21 e to the 3x equals 42. Divide both sides by 42. And that gives us, divide both sides by 21. That gives us e to the 3x equals 2. We change form, and that gives us ln 2 equals 3 to the x, and x equals the natural log of 2 divided by 3. You can then plug that into your calculator, and when we plug that into the calculator, we get that x equals 0.231. Log base 5x plus 1 plus log base 5x plus 3 equals log base 5, 48. We start off by combining these two. That gives us log base 5 of x plus 1 times x plus 3 equals log base 5 of 48. Since we have a single logarithm on both sides, we can now drop the logarithm and get that x plus 1 times x plus 3 equals 48. We multiply the x plus 1 and the x plus 3. That gives us x squared plus 4x plus 3 equals 48. So x squared plus 4x minus 45 equals 0. That will factor to x plus 9 and x minus 5. And so the two answers that we get as possibilities would be negative 9 and positive 5. Now the problem is when we plug these into the original equation, right, you always have to check your answers. If I plug negative 9 in here, negative 9 plus 1 is negative 8. That does not work. You are not allowed to plug a negative in. So we just have, when we plug in 5, 5 plus 1 is 6, that works. 5 plus 3 is 8, that works. So 5 works for both of those. 5 is a good answer. Negative 9 is not. Okay, exponential growth and decay. You're offered a job making $40,000 with annual 2% raise. Modeling function, variables, what will you be making after 10 years? All right, first of all, the variables. This is x and y in just plain English. So x, or whatever you use, actually we're going to use t, is going to be time in years. That's all I'm asking for. What does your variable mean? And then we'll say that A is the amount made in year T. So when it says variables, that is just putting in words what the two different variables are. No equations, no weirdness, that's it. So now how are we going to model this function? So we're doing an annual 2% raise. If you look back in the notes, we have several different exponential modeling functions. So if we have an annual raise of 2%, that means that at the end of the year, we get a 2% raise. That is our most basic exponential function. So a of t is going to be p times 1 plus r to the t power, where p is the initial amount, r is the rate of increase, and t is the time in years. So in this particular problem, that gives us a of t equals 40,000 times 1 plus 0.02 to the t power. That is the modeling function that we were looking for. What will you be making after 10 years? We just plug the 10 in, so A of t is 40,000 times 1.02 to the 10th power. I plug that into my handy dandy calculator. And I see that A of 10 is going to be 48,759.78. The average price of a hot dog was 80 cents in 1970. Due to inflation, the price has been continuously increasing at a rate of 4%. So here we have this word continuously. That means we are using E on this problem. Let's start off by quickly defining our variables. Now that was quick. T is the years since 1970. So notice when I define this variable, I'm not making T the year. If I did, I'd be using these huge numbers and I'd get giant values. I'm going T is the years since 1970. So in 1970, T is 0. There are several reasons that I do that, and I'll talk about them as we model this function. A of t is the price of the hot dog in year T. So what we have now, because we know that it was 80 cents in 1970, that actually gives us our 0 point. That is our initial condition. Because we defined T to be the years since 1970, we can make this function quite simple. So we're going to have a continuously increasing. So that's that A equals PE to the RT formula. Our initial condition is 0.8. So A of T is going to be 0.8 E to the, now it says that we are increasing at a rate of 4%, so that's going to be 0.04 T. That is our modeling function. It then asks, when will the average price be $2? So 2 equals 0.8 E to the 0.04 T. Now we just have to solve this for T. So we divide both sides by 0.8. That gives us 2.5 equals E to the 0.04 T. I take the natural log of both sides because I'm dealing with base E. Natural log 2.5 equals 0.04 T. By using the natural log, the E and the natural log just cancel out. Divide both sides by 0.04, and we get that T equals the natural log of 2.5 divided by 0.04, 22.9 years. So we'll say that T is 23. And so the price of a hot dog reached $2 in 1993.